So the title of my project is Evaluation of Rapid Brevetoxin Tests for Use in Shellfish Regulation, Industry, and Aquaculture. So it's not directly about aquaculture, but it's about an issue that greatly impacts aquaculture in Florida. The word Brevetoxin in the title refers to the toxin that's produced by the Florida red tide organism. If any of you are from the Southwest Florida area, you're probably familiar with red tide. I hesitate to use that term, but it's very familiar to most people. It's a very generic term that refers to many different types of harmful algal blooms. But when we say red tide in Florida, we're specifically referring to blooms of the organism pictured here. It's a marine dinoflagellate named Karenia brevis. Blooms of this organism occur almost every year in Southwest Florida, and they cause a wide range of environmental and human health impacts. One of those impacts is shellfish poisonings. And the first documented reports of shellfish poisoning go back to 1880, but they undoubtedly occurred prior to that. Wasn't until 1947 that the cause of these recurring events was identified. And it's undergone several name changes, taxonomic revisions throughout the year. So in older documents, you might see it referred to as Gymnodinium brevi or Tychodiscus brevis. So we knew what it was in 1947, but the toxins themselves were not identified until 1965. And once that happened, the state began to monitor for the presence of these toxins in shellfish. The reason we monitor is because bivalves are filter feeders, and when we have blooms, they can accumulate brevetoxins in their tissues. Should someone eat this, they could get what is called neurotoxic shellfish poisoning, or NSP. And I've listed some of the symptoms here on the slide. Typically, onset is a few hours after eating. We had a couple cases this year, and I think it was like 5 hours after they ate their shellfish that they got sick. In mild cases, people would experience chills, headache, general GI distress, abdominal pain, and maybe muscle weakness. In the more extreme cases, paresthesias is very common. They may have a loss of muscle control. Brevetoxin induces this rather unique symptom where cold things feel hot to the touch, so this reversal of hot and cold sensations, or they might have difficulty breathing, talking, or swallowing. So we monitor shellfish harvest areas in Florida for the presence of Karenia brevis, and when cells are present at or above a certain level, 5,000 cells per liter, shellfish harvest is banned in those areas. And that is obviously necessary, but it can cause a lot of negative impacts to the aquaculture industry and to oystermen. Obviously, there can be a loss of income or profit to these businesses. There can be an increased mortality to their product, generally not due to the bloom or the toxins it produces, but because if the clams aren't harvested, they just continue to get larger and they can exceed the optimal capacity for the bag or the cage that they're grown in. Also, I'm informed that when the product gets too large, it decreases in value. When customers can't get the product they need because of local closures, they can find other suppliers. And when employees of clam farmers can't work, they may find other jobs. So there's a lot of different ways in which they can be negatively impacted. And I know there's people in this room who've done pretty thorough studies on what those costs look like and the different ways that can happen. It's important to reopen these areas as quickly as possible after we have a closure. And here's where our problem lies. There's one approved method for testing for NSP, which is a required step to reopen after a harvest area closure. And it's called the NSP bioassay. And that has a lot of drawbacks, but probably one of the bigger ones is the delays caused in reopening because we have to use this one method. So it takes us 2 to 3 days after the shellfish is harvested to get results back so that management can reopen. Also, it's a pretty involved process of sample preparation, and that combined with the duration of the bioassay limits the number of tests that we can do in a week. There's also very limited access to testing. There's only 2 labs in the United States that can do this test. And it's costly, both in terms of labor and the materials. Also, the method's more than 50 years old. It was developed in 1965. It's completely archaic. And there's clearly a need for more modern test methods that are faster, enable more samples to be tested, that are more user-friendly, less expensive. They can certainly be more specific and precise, but they have to be equally protective. I forgot to mention it on the previous slide, but in Florida, all the cases of NSP we've had have been due to illegal recreational harvest of bivalves or from recreational harvest of whelk and conch, which are not monitored for NSP. There have never been any cases due to legally harvested shellfish to bivalves. So the monitoring program is quite successful. There are a number of different methods available for brevetoxin detection that people use today, but there are also a number of obstacles for getting any of these in place in the management program. Probably the most significant problem is the complex metabolism of the toxin itself. It's actually a family of toxins, so I may say brevetoxins with an S as I'm speaking, because it's what I usually do. So the organism itself produces at least 9 different forms of the toxin, and they can be present in the cells and in the seawater. When shellfish and other animals take those up, they get transformed into literally dozens of other compounds. So knowing exactly what to look for, what we want to monitor, is not straightforward. Also, all these different forms have variable toxicities. So comparing an analytical method to the bioassay doesn't often have beautiful results. Another issue has been that the path to method approval has not been very clear. So in the US, the Interstate Shellfish Sanitation Conference establishes the regulatory guidelines and procedures for the National Shellfish Sanitation Conference. For the National Shellfish Sanitation Program. And that's a national organization made up of federal and state shellfish management authorities as well as industry members. And until very recently, they couldn't tell you what you needed to do to get a method approved. Fortunately, that's a problem that they have resolved. And it's also, I think, a reason we've made very slow progress on this particular method or this particular toxin issue is because it's a localized issue. Outside of the Gulf of Mexico and the states that border it, it's really nobody else's problem. It doesn't get the global attention that some other algal toxin problems do, like saxitoxin. Regardless, after a really long and terrible red tide in 2012 and 13, in which we had prolonged harvest closures and several aquaculture members went out of business, we decided we had to actually take a stab at getting something done here. Of all the different chemical and biological methods that are available that people use right now to measure brevetoxins, there's a test called an enzyme-linked immunosorbent assay, or ELISA, that has performed very well. So we decided to evaluate 2 commercially available brevetoxin ELISA kits, and we focused on some of the more important species in Florida: hard clams, sunray Venus clams, and oysters. These types of assays use antibodies to recognize the toxin, and in this case, the antibodies recognize a portion of the molecule that is shared by many of the most prevalent toxins. So what we get is a sort of sum total measurement of the most common toxins in shellfish without really knowing which forms are there. One of the most biggest benefits to this method is that we can use a really rapid shellfish extraction method, do the test, and get the results back the same day that they're received. So after evaluating 2 commercially available kits, we zeroed in on one that's produced by a company called Marbiog at the University of North Carolina in Wilmington. And we just did a single lab validation according to the specifications laid out by the ISSC, because we're strictly going for method approval by the ISSC. And there's 2 components to this. One is pretty straightforward demonstration of assay performance using each sample matrix that you're looking at. And the kit that we looked at performed very well. I'm not going to go into great detail with the validation itself, but if we add toxin to the shellfish, we recover the toxin from the shellfish. The other thing that we had to do was compare it to the existing method, and that's where it gets a little more complicated. We did that with more than 500 shellfish samples, most of which came from our actual NSP management program, but a lot of them also came from industry who provided samples just to help us meet our goal and get this done. You can see we had plenty of hard clams and we had plenty of oysters. Sunray Venus clams we get far less often, and most of the ones that we tested as a part of this study were harvested during red tides specifically for this study, which is why you see the percentage that fail. This is passing by the current method, failing by the current method. 58% of our sunray Venuses failed because they were harvested during a red tide. What we usually see is more along the lines of 25% failure. More often than not, if you look at our historic data, these samples pass. And that's a problem because when they pass, there's no number associated with it. It's just a pass. So it's hard to compare that to a more sensitive quantitative method. Nevertheless, we had to do it. And on here you can see the green is just the range of concentrations we measure in samples that pass, and the red are quantitative results where they failed, comparing bioassay versus ELISA. And on here, what I really wanted to point out is that the clams had a smaller range of values in those that passed than the oysters did. And it was a little cleaner relationship, but I don't think that's a species difference as much as the fact that farmed product is more naive. It's not out in repeated blooms. Not all our clams, most of our clams were farmed. All of our oysters were wild. Wild product is going to have higher levels, more persistent levels than the farmed hard clams. And as we were doing this, we also were in communication with the FDA, and they sort of explained or suggested that this method would not be approved as an outright alternative to the bioassay. So what we did was took a different approach, and we used these comparative values to derive thresholds that represented levels no more than half of the regulatory limit and lower than the lowest level that would fail by bioassay, so yielding no false negatives. And those thresholds were roughly 1.6 for clams and 1.8 for oysters. And what we submitted to the ISSC was a proposal to accept the ELISA as a limited use method. We would be able to test samples. Should they pass by be at or below this threshold, they would be good to go. Your samples would pass. If they were above that threshold, they would have to go back and be tested by the approved method, or they would be considered fails. And while we do have quite a range of overlap between the pass and the fail, you'll see that there's clearly a lower limit to the amount of toxin that we see in samples that fail. So, and that's around 2.1 ppm for both types of shellfish. So I think that this is a very conservative approach, and that'll be very successful. If we apply this to the existing data, as designed, using the thresholds, 100% of the samples that failed by the bioassay would fail by ELISA. And of the ones that passed by bioassay, 63% were below the threshold. And had we had this tool available for use over the last few years, it would have eliminated the need to do half of the bioassays, and probably more, because if they fail and the levels are high by ELISA, we would not have gone back to do a bioassay. And so we did this to try to get some tool into place in the management program, and this is where we stand at this point. So we've learned an awful lot about when you test BioELISA, whether or not it's going to pass or fail a bioassay, so we already use it. We'll screen samples submitted by FDACS, who is our management authority. And if the levels, this way we can better allocate the very few number of tests that we can do by the approved method. We do have a proposal submitted to the ISSC that they're going to discuss that and vote on it in a couple of weeks, so please wish us luck. And we were also able to use our success in this project to leverage NOAA PCM HAP program. They have recently provided funding for us to take this to the field, to the program, use it to implement the method, and also to transfer to other Gulf states via training workshops. That's about it. I just want to thank Sea Grant again for helping us make this possible.